Hi everyone, I'm Yicheng from Bucknell University. Today I'm going to talk about my summer research project, particle swarm optimization for high-rigidity spectrometer. The goal of my project is to find reliable sets of optimization parameters for the system and to maximize the transmission rate of the fission fragments to take full advantage of the particle beams. These are beams of rare isotopes being used in experiments to understand nuclear structures and astrophysical processes like as supernova. HRS is an ion optical system that can pass the particles beam through magnetic fields, just like passing the light beam through lenses. And HRS measures the properties of the transmitted particles. For my work, I try to optimize the system in fifth order because there are some high order aberrations that might lower the transmission rate. The upper graph shows a rare envelope of the first order system, which ignores the aberrations, and the lower one shows the fifth order, more realistic one. Since the system hasn't been built yet, we simulate the system using cozy infinity because it's able to simulate in higher orders. We use particle swarm optimization, or PSO, to optimize the system. The basic principle is that the particle swarms are searching the global best position just like birds searching for the food. The swarm members are attracted to better regions when they communicate with each other about their past experiences. The goal of the optimization algorithm is to lower the objective values as much as it can. So we set the objective value equal to 1 minus transmission rate and look for the most reliable settings of parameters, acceleration and inertia. We first explore a wide range of parameters and found the setting 0.5, 0.4 worked well. We have some examples of how swarms search for the global best in different settings. Then we explore the parameter set space around 0.5, 0.4 as shown in figure 3b. We analyze the best 80 and 60% of the data collected because we want the setting to perform well most of the time. We convert the data into a plot of the mean and standard deviation of the objective values and also the final parameter spaces, as shown in figure 4. From that, we conclude that the parameter space of PSO differs according to different initial HRI settings. We found two best parameters for the center energy tune and one best setting for the highest transmission energy tune. We show that we are able to improve the transmission of fission fragments by 30 and 10% respectively for these tunes. We will continue working on the same testing for more HRI settings and on different systems in the future. For example, we started to use this approach to minimize the beam spot in the high transmission beam line